let's see, so I wanted to go through a couple things. So the homework, I guess, let's see, any questions on this? There were some questions that came up. Oh, let's see, one person asked, let's see. Let's see, about the, I think. No. What for the TG? There's something about block copolymers in here, right? Isn't it the same thing? Here, yes, C. So somebody asked, like, they didn't see this business like in the notes or anything, or in the class recordings. But basically, so this is just coming from the thing I didn't open here. The last set of notes. So slide one, this thing. That thing downloads so fast, like when you're here. These are like, it's 100, I don't know, it's 50 megabyte or something. And just zip. Anyway, so I went through like, so this is slide 110 or something. 110, and it goes through block copolymers. And this thing, this is the derivation. So it's basically, you have like the interfacial area A, and it's got a thickness dt. And then there's an energy because you have like 9 meeting there. So it's like an energy. So it's going to be the chi parameter times the volume of that unit. So chi's energy per kT. So you multiply it by kT. Then you multiply that by the ratio of the area to the area of the entire chain. Or the area of 1 unit. Chi's per 1 unit. So it's a volume of 1 unit. How many of those 1 units are in that interfacial thing? That's what it is, the number. So chi's per unit of the chain, per kT. And then, so you need to know how many units are in that interface for the A and B mix, or the styrene butadiene mix. You have the area times the thickness divided by this volume of 1 unit. So basically from that number, then everything area. I guess they assume that the thickness is fixed and the area can change, meaning that the area is like the packing length, like how the chain can pack into space. So the packing length comes right. This is the first time anybody had to think about what the lateral size of a polymer was, which is kind of more or less what the packing length is. Right, so maybe, I guess the question is asking you to just go through that somehow. So it's a bit balanced in that energy, the elastic energy to stretch a chain. It's like it's always, all these things are always going to be that elastic formula that we got. The derivative of the energy of the chain with distance, the elastic modulus. So take that elastic energy just somewhere here. The elastic energy is like this thing, 3 kT over NL. And then so basically this is the elastic energy. And you sum up that interfacial energy, which wants to demix, and this elastic energy, which kind of restricts the length of the thing, and then take the derivative with respect to the A, which is more or less, the A is more or less the packing length for the chain. So that the packing length fell out of this. Then Witten, after he did that and got these numbers, he realized that the packing length was some number that could have some importance. So then the importance they came up with is this thing, which is that the modulus goes with the packing length to the -3 power. Okay. And it comes out, right, and that's on slide 116. So the whole thing's, the C is here. It's like 110 to 116. And then he in this paper, so in the supplemental to that paper, let's see, somewhere he shows a plot versus packing length. Here, it's a log plot of packing length. So I digitized this and figured out that slope was packing length to the -3.3, like that line. He must say it in here somewhere, but anyway, I just digitized it and like got that. So you can also, if you want to if this was in full decades, it'd be easier to see, but you count how many decades. So it would be like for 1 decade, you get 3.3 decades up over on this side. So for a slope at 3.3, like when you have a log plot to get the slopes, you do how many decades by how many decades, or how many orders. Anyway, so 3.3 is almost the same as like whatever that thing is. So the thing about them. So basically, it's saying that he's saying that the glass transition, saying that the glass transition is proportional to the modulus in that case. And then why that is, I mean, he never says that, but that's kind of what that plot says. So if you see something like this is the G prime, the storage modulus, and then it's got a high modulus when it's glass, and then when it's a liquid, it's got a lower modulus, and there's a sigmoidal thing. And sometimes you say like halfway point is the glass transition, because it's going to actually be a range where it softens. Right? So anyway, so if you say this is the plateau modulus for the rubber, and in some cases these don't have a plateau modulus because they don't have like entanglements. In other words, you need entanglements, you can get a plateau modulus at whatever frequency they're looking at it. But anyway, this is a rubbery plateau over here. This is glassy. You know, like I said, the glass, like if you have a glass marble and throw it on the floor, it bounces. If you have a rubber ball, it bounces. And in between, if you get to the glass transition, it just acts like lead. It'll just stop. If you throw it, it just stops there. So it's good to demo, but I don't have liquid nitrogen. So I'm kind of bothered to go get it. But anyway, so anyway, if you think about that, you get in glass transition here, if you raise the plateau modulus, it kind of shifts the glass transition to the left. That's what I would say. Like I mean, it's a guess, but so if you raise this thing with P to the power -3, then as that raises the glass transition, that halfway point of the sigmoidal is going to shift to the left. There's probably some real explanation for it, but that's what I came up with going Cincinnati. So you might have a better explanation for why they get that dependence on P. So that's one thing. That was a question that came by email, but you guys get that part, or hopefully that's all right. They can answer that. Any other, did anyone do this, or do you have any questions?
For D in class, like you mentioned that there was like 3 different ways to get it, but I could only like find one. Do you feel like mention all 3, or is like one fine?
No, one's fine. Did I say 3?
Yeah, or maybe like broke through is to get it on like the wrong problem, and I was just confusing myself.
I mean, I'm thinking that so glass transition involves a motion of 9 units along the chain. That's kind of the definition people throw around. So when you get coordinated motion of 9 mer units, then you get the glass transition. That's one definition of it. There's also a volumetric definition, which is like basically you need like a 2 or 3% change in the volume. So if your volume expands with temperature and you reach a point where the free volume is 2 or 3% of the total volume, then you get the glass transition. In other words, it's the ground up coffee vacuum pack problem. Like it's like a brick, then you just let a little bit of air in, and all of a sudden it's like a liquid. It's squishy. So, but that doesn't answer what the Flory-Fox. So if you inverse of TG would say like the frequency, like it's a higher temperature, you get a higher frequency. So it's anyway, somehow the inverse temperature I got back with a frequency thing, but I'm not sure exactly how I did that. Why it's 1/T. I don't know why exactly. Maybe you can figure out why. And then why it's the weight fraction. That's kind of easy. Normally you'd use mole fraction to talk about thermodynamic things, but because say you put a plasticizer in the number of plasticizers is going to be a huge number of moles, but it's a polymer, so there's only like one of them there. You know, so basically if you talk about moles, it won't be a good number to use, the mole fraction. So the weight fraction is probably better. You know, in other words, they're going to weigh about equally, or the diluent might even be a lower weight. You know, so are much lower weight. So weight fraction makes sense on how you're kind of counting to put the thing together because it's polymerized, basically. The theoretical basis, I mean, I think you got to just fish around. There isn't an answer to that. Like, I don't think, like Fox didn't give a theoretical basis for it, I don't think. So it's just an observation. But basically there is kind of, maybe you can come up with a hand waving thing, something either to do with free volume or to do with frequency, like the vibration frequency of the thing. If not, it's okay. I mean, sometimes the latter questions in these are kind of open-ended. So any other stuff that you said? That's all right.
Then for E, when you were talking about like the mobility of chains, when I was reading the paper, I could only like see them talking about like mobility when they were like talking in terms of like delta. Am I like missing something? Which is probably like, I'm probably just missing something, but I can only like find it when you're like calculating the delta for like the mobilities of like all of like the atoms together.
He just says, all right, to determine, like he doesn't determine anything. He just says it's one with no units. Like it's just the number one. And he says it's for these aromatic rings, it's A times one. And then for the thiol rings, it's like 1.2 times A times one. And then he sums those up. It's completely like just free for all. It has nothing to do with mobility except in his mind. Like he hasn't measured anything. He's not correlating it with any experiment. He's just saying like an aromatic ring is going to have less mobility than an alkane side chain, which is true. It's probably true. I mean, it might not be true. I mean, you didn't measure it, so you don't know. But basically, it sounds like it could be true, right? So yeah. So the point of this is, he didn't. The word determine, is pretty loosely used here, and it basically one with no units isn't. Mobility is super loosely used, right? It's basically just making something up. All right, so it's totally in line with machine learning. It's exactly what everybody's doing right now. Like, so you get a slew of things that you know parameters for, and then you use some number to convert it to a common denominator value that you can plot against some property you're interested in, TG in this case, and then you look at a bunch of samples, which he did, and you optimize those numbers through iterations. So you change the weighting factors for all your parameters, like the 1.2 for thiol thing, and you just let the computer randomly or change those until you can predict the test set of numbers that you have. Then you go and see if it works for another set that you haven't looked at. So that's machine learning in a nutshell. So he does that, except he only has like one parameter. So it's simpler, and he only has like 25 or something learning set, and he never actually looks for it to predict. He says he's predicting for like some chemist can make it, but he doesn't actually test it with some real thing that wasn't part of his learning set. So, but basically the method he uses is exactly like machine learning. So it's just exactly what they do, except they do it a lot more complicated. So he mentions even in the front end, like what's up in question one, like all these things like group contribution, and then group contribution, machine learning. So, I mean, you can Google it. It'll kind of say what I said, I think. And then group contribution is earlier from the 1950s or 40s of what becomes like machine learning after, I guess. Although they don't say they have anything to do with each other. Basically, they're kind of similar. And there's no real understanding with group contribution. You just say, well, I mean, you say you want to calculate the density of an organic material. It's complicated, a lot of things in it, and you just break it down into the groups. And you say each one contributes density to it. So you sum up all of them with some kind of weighting factor. So it sounds like exactly the same thing, but it's kind of from the 1950s, right? So I think the so there were like real thermodynamics people, and there were like engineers or chemical engineers, that wanted to know because they had to make stuff. And they needed to know what the density is going to be of this thing. And so And the Dutch, like DSM was there, the chemical company, and the Imperial Chemical was there too. So they had a bunch of chemical companies in the Netherlands, and their universities kind of got tied in with them. And the thermodynamics people kind of went to this group contribution thing for a while. It's still around. Like if you look in the chemical engineer's handbook and you say group contribution, you can find a whole table of values for all the things to add together to get whatever you want. You know, and also the chemist's handbook, the rubber handbook has that in it, and the NIST thing has it too. NIST web book.
When you were talking, this kind of relates back to last week, when you were talking about group contributions, you said that they were only focused on one parameter of it, so it was kind of like a better interpretation of it, or?
Well, yeah, if you have a 30 parameter model and you can fit that data with one parameter, yeah, it means you should kind of understand what's going on versus the guy that has 30 parameters and just like fishing in the dark. So yeah, the fewer the parameters, the better your model. See, if you have one data point and one parameter, then that can work, you know, but you know nothing about it. If you have 10 data points and one parameter, it kind of gives strength to you or whatever you're doing. So he's got 26 or something polymers with one parameter. So that makes it look like it's kind of working out, you know. Yeah.
So the last part of E, like, isn't it intended to, was it an accidentally intended almost for She's definition of mobility to end up being linearly dependent instead of power law or exponential?
I don't have an answer for that question, you know. I mean, it comes out linear. Everything in polymers is log. Everything is a power law. And here it comes up with something in TG, everything's like exponential of something, like the Arrhenius function, that's TG. So I don't know why it would be linear, you know. It would seem like it should be exponential for TG. And if not, if it's a polymer thing, it should be a power law. You know, and he's got this linear dependence with his mobility. So yeah, all right, you're right. Maybe it's just because he summed things up linearly. So he just sums up the terms linearly, so he ends up with a linear dependence. That could be. I mean, yeah, you're right. So there's an assumption involved when he first gives that equation, right? Like at this step, this thing could have been any function in the world. That could have been a power law, a bunch of power laws. It could have been an exponential of something, right? So why it's a sum, and just because he uses the same symbol for mobility and mobility here, these aren't necessarily mobility. This is one and A, and whatever he had, you know. So this could be anything. So he has a linear sum, ends up with linear dependence. That could be part of it. I mean, there's an assumption involved once he says it's going to be a linear sum. This is one of the things when you do machine learning. So you're going to have all these parameters. They're going to have weighting functions on them. And then what's the functional dependency you're going to put in for those parameters? That's one of the choices you have to make. Usually in machine learning, it's a linear dependency you use, right? But basically, it doesn't have to be. I mean, if you measure the size, the density, so things are all different, and you have to add those different measurements you have together with a weighting parameter, but it doesn't have to be density, linear density. It could be size cubed, and then times a weighting factor to match it up with density, which is a volumetric thing, for instance. You know, so he's adding them up here. I don't know. That could be one reason why it ends up linear. Yeah. So you're right. Yeah, it's probably somehow buried in the assumptions, which he doesn't list. Like he never specifies the assumptions he makes, which makes it difficult to attack it. It means you have to come up with these assumptions to figure out how to critique what he did. And then that's actually the only step you need to do. Once you figure out what his assumptions are, you can see how his method could fail. Because he didn't even notice that he's making assumptions when he did that. But so yeah, so it's, I don't know, it's kind of thought provoking, I guess, the last thing, if you want to look at it that way. But it's kind of, to me, it's like weird that it's straight. When I looked at it, and it's like a straight linear dependence. And where is that? It's in here, right? Like this. No, this one. So first of all, TG doesn't, it depends on mobility. I mean, if this is really mobility, it depends on mobility. I think I'd have to like Google to figure out what the depends of TG is on mobility. So, but figure out, like search for that somehow. He might even say. Anyway, so that, any other questions on this thing? So anyway, that, I wanted to go through, you wanted to know about searching things, how to search things, you know, so that's something you could do, like, so I usually use Google Scholar. I never, like, a year ago I didn't, but now I'm kind of using Google Scholar all the time. So if you want to know like mobility and transition, something like that. So it's good for, this is good if you have a thing that you want to know about. Taking for independence, mobility near the glass transition, making glass transition to high mobility. It's almost the same thing, right? Conjugated polymers. Maybe that's a topic that people are interested in. I don't know, but thickness dependent mobility in glass transition of polymer nanospheres. Mobility in glass. That seems like something different. Molecular mobility. That's what I want. So you kind of have to find keywords when you do stuff. I want molecular mobility, not the, because they're doing sphere mobility, like the Stokes law for spheres. That's different. Molecular mobility of amorphous below their glass transition. Linking glass transition. So anyway, volume effects on the molecular mobility close to glass transition. I don't exactly see what I'm looking for, but that's kind of the first step I would use. I'd look for one paper that looked pretty good. Looking for structural state relations, that sounds pretty good. So I'd find that paper. That's kind of marginally close. You might get the title. I might look at the paper. So I'd look where the people are. So they're in France, and this is from 1998, so it's a while ago. See, there's some kind of weird dependence of these things, right? It isn't some linear dependence, I don't think. This is 1/10 relaxation time, which is related to the mobility, right? So it could be should be 1/TG, the mobility, I think, or something, you know, so that's what, so you can kind of see maybe, all right, so that's kind of how I start looking at things, just find something. Then I go to this Web of Science, which the only way I know how to get to it, like the UC thing. There's probably an easier way to get to this, and it used to be much easier to get papers and but I still kind of click through like that to get, because you need to get onto the UC so they let you in. And then it calls your phone. And then this thing's nice because you can, I'll show you how you use this. So sent to other options. I don't have that thing. I have a phone call. Oh, I shouldn't have said yes, this is nice, but good. All right, so you get into Web of Science, and then you can do, so it lets you search for title. So you can do all fields. And then you can do like topic, title, author, whatever. So I'm doing title because I got that title, right? So, and sometimes you can't just click and get the PDF of the paper, like, because usually it's locked out. And then there's a long process. But if you get the paper through Web of Science, it links and you get it right away because it already knows that you're at UC, right? So anything UC owns, you can get right to it. Back to 1980, something like that. So if it's older, if it's from the 1950s, then you have to go to the library and do Iliad. You have to send in a request to them, which is also linked to Web of Science. So anyway, so there's the paper, that paper I just looked at. So I want to know, like, so it's been cited 16 times in 16 other papers since whenever it was published. I don't see the year here, but whatever year it was published. And they have 15 references in it, right? And if you want to get the text, you click this, it goes to the publisher. And there's like 2 links. I'm not sure what the difference is, but basically that one kind of works. And if it doesn't have that, it'll have a link to Iliad, so you can make a request to the library for the paper. So it's kind of useful. And then so you can do a lot in here, but basically you're going to use this thing, the 16 people that says this, I think, is an old paper. Oh, 1998. So like, and you want to know the same topic, and assuming that everyone who wrote about something on that topic cited this paper, which may or may not be true. So the better the journal, the more likely that is. If this is like Nature, then everyone will have cited it because it improves their journal citation because everything's web like that, cross-reference thing. So anyway, so this is Journal of Non-Crystalline Solids, which is it's a pretty good journal. It's like kind of lower mid-range journal. You know, so the 16 probably aren't, this is probably isn't the best paper to get for it, although it's the topic's appropriate for it. So you can go here and then you can this is all the papers that cited it. Then you want, like, if you want something more recent, well, 2016 isn't doing you much good, right? You can figure out, like this one, figure out one that's got 40 citations, 2006. And it's in Physical Review Letters. That's like one of the top maybe 5 journals, right? So that's a good place to look. That's why it has 40 citations. And then you can fish around. So there's one that's got 50 citations in the same journal. So here's my theory, you don't know, but so, and that's from 2000. So a couple of years later, it looks like the same French guys maybe. Relaxation, non-crystalline under mechanical stress. And then the one that I have that's got 40, characterization, drastic increase in molecular mobility of deformed amorphous polymer. So it doesn't sound exactly right, but anyway, so if you get that one, 2006, so then you're going to get like more recent, if that was the right thing. So this is 2021, so it's getting closer. Viscoelastic mechanical relaxation. So you can kind of fish around. It allows you to kind of go. So if you were really doing this, you'd like take every paper and look at it like you do view text. Is that, I think that'll open the window. So then takes you here, and then you have the paper right away. You don't have to do any fishing around to get the paper, right? So that's good. And then you can go, so basically you're going to end up with a lot of windows open. And then if you, so you can kind of look, take an old paper and look forward, or you can take a new paper and look backwards. And if you look backwards, you go through the ones that they cited, right? So they call it web of science. Everything's like connected by citation. And you can, so if you explore that web enough, then you know everything about it at some point. And that point is indeterminate. It's basically you just search and search and search until things start repeating. Well, I've already seen that paper and that paper. Then you know you're pretty much at the end. Like when you see like 2 or 3 that are the same, then that you're done. So that could take years, or it could take, it depends on the subject. You know, so usually getting something that's published this year is pretty helpful. Like if you can find something that's published this year, it's like a helpful thing. So both things, like the Google Scholar is a good thing to start out with. And then if you want to get like more and more into it, then you use this thing. And it's got, even you can go to the person. This one's dynamic relaxation, actually probably some metallic glasses, 258. So that's a pretty good, that's like a high citation. Anything over 100 is a high citation, right? So then you could look like you, and that's, oh, it's got an award, highly cited by Web of Science. Anyway, you can look at the person too. So you want to know about people, and then you can go like this guy, whatever he published. So he's got H-index with 50, he has 50 papers that have 50 citations on it, which is good. That's really good. It's like National Academy level. I mean, approaching it at least. And then total publications 278. That's good too. So like anything over like 150 is pretty good. And then you can go here. This is all his publications. Most recent is this year, observation, and it's all about the same stuff, I guess. So then you can do citation report, and it'll give you like, that's how he's publishing. So he went into administration for a while, and he's back into research, something like that. Or he got cancer, and then he recovered from it. So his life story. he was born and then he published by that time. You know, so anyway, so you can see that, and then it also lists like all his papers here by how many, so his best paper has a total citation of 1,000. So anything over 1,000 is like a seminal paper. So this thing from 2012 is a seminal thing. And then he's got 2 papers that are over 1,000, so that's pretty sweet. It's all about Lassie and whatever, the same subject, right? So this is how you look at people to see, like if someone's giving a seminar, put their name in here and just go look and see what they're doing. You can see like, oh, they just started doing more stuff, something like that. Right? So it's pretty useful for that reason. And then also, so you get the citation report and you can look at what they say. Like usually you sometimes say like he's published 248 papers. And you can look in here, does it agree with this or not? In other words, are they making it up? You know, so you can say like they've counted some things that aren't papers as papers. You know, so this is only the papers that are peer reviewed. So I don't know if that helps. You know, if you want to, I don't know, you could try to fish around this. And she's doing with the project with Malbing too, right?
Yeah.
Yeah, so, but if you guys, whatever you're doing, I can help you do the search if you want.
I'm glad you showed that, because I didn't know that this was a resource that we could use.
Yeah, it's pretty sweet. I mean, I use it all the time, but it is like a lot more. All right, so the Google Scholar basically give you an overview, and also in Google Scholar, you can pick like only things published this year, you know, that type of thing. You can do that in here also, but it's more involved because it's more powerful. So basically, this is going to take more of an investment to get in. Just literally like put your stuff in. It'll come out with some stuff, maybe not everything, but it'll give you some. And if you can find a thing that's exactly what you like, then you go back to that paper and then put it in here. And then do like an in-depth thing in that paper. And then you can, usually you'll be able to find the tracks back to like everything that exists on that subject. You know? Otherwise, it's a mess, you know. In the old days, so in the 1980s, 70s, then there were like in Polymer's, there were 3 journals. And everybody published in those 3 journals. And if you visited someone's office, they had all the papers they published in hard copy. And they'd hand you a hard copy of it. Like when you publish, you get like 100 copies of it. So then that's how things were like transmitted, you know. And if you wanted to find stuff, a search like this, you went to the library and you found the chemical index or something. And there was books of books of books. It would take you like forever. And you never were sure you got everything, you know. But basically, everyone in polymer science were reading like Macromolecules, Journal of Polymer Science, Polymer, maybe a couple other journals. You know, they read every article that came out in those every week. Just like people read a lot of journal stuff. Like Jim Mark was a faculty's dean in chemistry. And I would go to the engineering library on the weekend, and he'd be in there like literally reading the journals, like just not looking for anything, just reading them. You know, so like that's kind of how people operated. Anyway, now no one does that. So basically, maybe someone does it, but I don't know anybody that does it. So anyway, this is like these, and also you don't publish in like one journal, like you'll find Polymer, like this week's in Nature. So they're all over the place. So a lot more Polymer journals is like, you know, 20 of them or something. So instead of literally like you walk into people's office and they would have all the journal, every journal on their wall. They'd have a bookcase full of the journals, you know, so if they were serious about it. So anyway, that doesn't really exist. And if you wanted something, you'd want to like ask them for a copy, like your advisor, you'd go in and get a copy of the journal, like the actual journal, and take it back to wherever you're studying. And if it was one of their papers, they'd give you a copy of it. You know, so anyway, now it's different, like it's all here. So basically it's kind of easier, but people don't use it as much. So you find out like people don't even read it, even though it's so accessible. No one even looks at it. So mostly you can easily find where people haven't cited exactly the same thing was done a couple of years ago. You know, so anyway, that's how things happen. The easier it gets, it's like the computing power, then nobody knows how to program. It's like weird. Like in the days when there were no computers, everybody knew how to program. You know, and then like as computers get more powerful, then like no one knows how to do it. So it's the same kind of thing. This is kind of a strange thing. The easier it gets, the less people get lazy or something, I guess. Maybe it's just inundated with too much. All right, so that's that stuff. Hopefully that's okay. So I think maybe do your own thing and I can help you if you need help with it, you know, and you guys, but so. All right, so that business. All right, so I'm gonna get rid of that. Any other things on the homework or that, that's it. All right, so I want to go through some more of these things. So I basically kind of go through what I went through last time. So, and it's good to start on the, because everything is linked back to the van der Waals equation, the subject of the excluded volume. Like, it seems like this is the, and whenever you find something that's complicated, you can't understand, the root of it is always back at this point. So it's really good to kind of keep an eye on this business, which is fairly simple and things can get really complicated. So you have ideal gas law, PV, basically usually you talk about specific volumes as just RT over V, like molar volume. And then first thing you want to have, so you want to have this idea that you can't pass through itself. So you have an excluded volume, this B. So you just kind of say the volume minus B. And that's going to serve to increase the pressure. So the fact that you can't pass through yourself means the pressure is going to go up, right? And then if you want to have phase, so that won't give you phase separation. And what you want from an equation of state is a phase separation, so you can predict miscibility limit, right? So the only way to get miscibility limit is if the things can cluster together, right? And is not going to make them cluster, it's going to have the opposite effect, right? So if this increases pressure, you need something that would decrease pressure. So you add a term and it's a binary term. So the simplest kind of interaction is binary. I mean, you can't interact with one, so you have to have two. They attract each other. It's going to lead to phase separation. So you say it's going to decrease the pressure, negative. You have an enthalpic interaction, and then you have this density term. So number per volume is the density or concentration. It's binary, so it's a concentration squared, right? So that would be nice. That works. That works almost for everything. It's kind of surprising. It's like a Arrhenius function. Like,
what would be an example, going back to when you modify the excluded volume, what would be an example of excluded volume?
like a sphere, if you have a sphere, so you have the sphere's volume. And then if you go out another sphere diameter away, then that entire space that it would include is the excluded volume for a hardcore sphere. It's 8 times the volume of the sphere. It's kind of like, it's more than 2 times the sphere because it ekes out all the volume in 3D space. Right, so that's kind of like the basic excluded volume. That's the one van der Waals had in mind. Right, if you include this, so that volume could be more or less depending on if the thing's charged, like a repulsive, it's a positively charged colloid, and basically you have a bigger excluded volume. It could be a soft potential, that's a hardcore potential. So you can put a lot into it, but it's going to have the same form. It's going to be the same thing. Right, so then this attractive thing is also going to be the same form, but you could have things like, that's a potential, it's a binary potential between 2 things that are attractive, but it could be that it's got, in other words, 2 things attract, they can also organize. So it could have like an entropic part to it, and then it's basically an enthalpic term first, because you have temperature isn't, so anything that depends on temperature is entropy. Like basically, temperature dependent terms are going to be entropy, and non-temperature dependent terms are enthalpy, right? So basically this is entropic and that's enthalpic. But you could have enthalpic that affects entropy. Like if you have an attractive thing that makes it order, this term could have a temperature dependent part to it that involves, and there's other ways you can have temperature dependence to attraction. All these are relevant to polymers, believe it or not, because polymers is just an example using this thing, right? So what you want to do is this, you have the other way to look at this is you say you have the compressibility factor PV over RT, which would be 1 for an ideal gas. And then you do an expansion in density. So you say to the first order, so the first viral, it's called a viral expansion. The first portion is 1. And then the second one is this B2. You do with binary interactions because this density times density is density squared. So that's a binary interaction term, like the A term in the van der Waals. So then you have 2. So this is just an engineering approach, like a power series expansion approach to this idea of the equation of state. So you have 2 equations of state, this one and that one, and they're both involving P. So you should be able to write it, this thing in the format of that thing, right? I guess this thing didn't update this. Oh yeah, it did here. All right, so. All right, so in order to do that, so you have this weird form, right? The van der Waals form, which is kind of weird. It doesn't look anything like the power series form, but you do this. If you take, so if you define Z from the van der Waals, you multiply P by V, divide by RT, RT comes out, then you have V just multiplied here. So PV RT, so V comes out as a front term, RT is out. This is molar volume, so the N's gone. B minus B, and B is also the molar excluded volume at that point. Right, so, and then this term has A, so A doesn't have a T, so you don't have to worry about the RT for the A, and you just have rho. Like this thing is rho, you've taken a rho, 1 over V is rho, so you end up with a rho here. So this term, this looks like the second Viral coefficient, this A. So A and B2 have something to do with each other. We have this kind of nasty term here, right? So if you divide everything by V, you get 1 over 1 minus B rho. And then if you realize that that's the answer to a geometric series. So if you have A over 1 minus R and A R to the K summation, and then K goes from 0 to infinity. So the terms would be like R to the 0 is 1, so A, then A times R, A times R squared, A times R cubed, that kind of series is going to just equal 1 over 1 minus R. And R is rho, and rho is much less than 1. That's like the number per volume. It's the number of kind of mer units per volume of the chain, and it's a low number, right? So in terms of the power series, this thing, yeah, you only need the first two terms, or you could include the third term if you want to get complicated, right? Because if rho is 0.1, this is 0.001, then 3 would be like some really small number, right? So you can forget about the higher order and you just have these. So if you just include the first two, then you can plug that in up here, where you had like A times rho, and this is B times rho. So you have you end up with B minus A over RT. This should have been A over RT here. Sorry. A over RT there. So it's A over RT, B minus A over RT is the second Viral coefficient. Like 1 plus rho. Viral expansion, whatever that is, 1 plus B2 rho. So B2 is that B minus A over RT. And if you want to include the third one, then you have a third Viral coefficient, which is like B squared, if you do that. Right. So anyway, so basically you end up with that form. That's important to us because we're going to measure, we're going to look at excluded volume and then enthalpic modification to it to see the temperature dependence of this excluded volume. I know this B2 is an excluded volume. It's got to do with the second order of the binary interactions in a Viral expansion, right? So it has a van der Waals A in it. So minus A, that's a part of the excluded volume. That's a temperature dependent excluded volume. And then there's a hardcore excluded volume. So you have like the hardcore, B2's B, and how it's modified by the attraction, which makes a smaller excluded volume and a larger pressure. So it makes sense. Anyway, this makes the same sense as that, except it's kind of simpler to deal with this. B2's units are volume or molar volume, and B's excluded volume, and then that's modified. You can think like, if I have a repulsive potential because it can't pass through, it's possible to have a temperature where the attractive potential could equal that. And at that point, the balls act as if they pass through each other. They become invisible. There's a temperature where the balls become invisible, the spheres become invisible. So that temperature is where this B2, so B can't go to 0 because it's a hard core, but B2 can go to 0 at some temperature. So that there's like, where B2 equals 0, so RT's A over B. Right, so we have the enthalpic interaction over the hard core gives you a temperature, a magic temperature, where at that temperature, the repulsive hard core thing, preventing it from phase separating, is overcome by the attractive part that makes it phase separate, and then it comes out of solution. So low temperature. So you cool it down, temperature gets small, then this negative term becomes more important. At some point, this number goes to 0. So that magic temperature is like the critical temperature for it. Right? The idea you have something minus something by T gives you a critical temperature right away. Right, so it's a nice little ditty. Right? You start with this thing, should be fairly simple to understand. Then you take an engineering expansion of it. You find this magic new excluded volume number for binary interactions. And then it has a magic temperature falls right out of that, this critical temperature. So we'll find out that's exactly the form that Flory-Krigbaum came up with for this excluded volume. It's exactly like this, right? So it's directly, so they knew well this whole thing. So they were anticipating something like that, and then they got that when they, so basically they had the answer, and then they figured out how to cook the books to get it. That's why it's important to kind of say that here. So how they did that. So they knew Boltzmann should apply because it's a thermally equilibrated system. So everything's flying around. The probability of some kind of end-to-end distance has to have some energy. And then by KT, that would describe the probability of a kind of things flying around operation line, Boltzmann probability. And they also had this probability that we got from integrating the Gaussian function, something, right? This is the Gaussian function, right? For the probability of the end-to-end distance. I think we worked that out already. So anyway, the arguments that the exponentials have to equal each other, then you can get the energy from that. The energy of a chain at some temperature that's randomly arranged on the coils. And then this is the end-to-end distance squared, and this is the calculated end-to-end distance. So energy is the distance. As you stretch it out, the energy goes up. And then, anyway, that explains the energy of the chain. Right? If you take the derivative of that with respect to R, then you can get the force and the spring constant. So the two's R derivative would be 2R, that cancels with 2. So spring constant is going to be 3 kT over the molecular weight times the Kuhn length. So that's repeated like over and over and over again. Everybody uses that. The energy term you use sometimes, but the spring constant term, in other words, the plateau modulus, it's like the G0 that you measure on the dynamic measurement, the plateau thing, that's going to be proportional to the molecular weight between entanglements. If the entanglements are causing the modulus, then it's got to have an inverse entanglement molecular weight dependence. Right? Same thing for a rubber. If you put in N-link chains and polymerize it into a rubber, then the modulus of the rubber is going to be proportional to 1 over the molecular weight of those N-link chains that you put in. Right. So every time you do anything, and then even with the block copolymer, this is the elastic energy that was used to balance the mixing energy of the surface. So every time someone does a calculation with polymers, like that equation shows up. This energy equation, just as a comparison between Gaussian and the Boltzmann factor. Right. So anyway, in this case, if you want to know about the exclusion of so the exclusion, say, of 1 unit of volume VC over the entire coil size of R cubed, that's the exclusion. And 1 minus that, so this is a really small number. And 1 minus that is going to be almost 0.999, a lot of nines, right? So this is a number near 1, right? And then if you want to include all the other binary interactions in it, you raise it to the number of those binary interactions, number of pairs. It's going to be n times n minus 1 divided by 2 factorial by probability. Then you can just call it n squared over 2 because n's like a huge number. Right. So you have that kind of probability of exclusion. And then if you take a log of that and you take an exponential, you get the same thing back. When you take a log of something to the power comes out front. Then you end up with this expression. And if you look at the 1 minus something, like exponential of x is 1 plus x plus some other things. If x is small, you can forget about the other things. And x here is VC over R cubed, so it's small. So it means 1 minus is like exponential minus x, right? So basically, if you take a log of that side, so log of that is basically that argument. So you get n squared VC over R cubed divided by 2. That's the probability of exclusion. And it's of the same form exactly as this energy. So it's going to be exactly the same if you compare that with the Boltzmann, so basically you just add that in, right? So you just add this term in, and then you get this expression, which is the original expression, and then added to this expression, because it's negative for the Boltzmanns and negatives cancel. So you just have that summation gives you the energy of the excluded volume change, right? So you can't, so you normally want to get what is the end-to-end distance, r squared, so you'd integrate this with respect, so integrate r squared times the probability based on this, right? So it's like, get this probability, then you do integrate r squared times that and find out what's the mean r squared, because this is a weighting factor, that's r squared. But you can't integrate like this guy, r squared times that, you can't integrate. But I showed you before, the derivative of this function gives you the 1/2 end of the 1/2, the same scaling behavior, but a different prefactor. So the idea is you could differentiate this, get the peak value, and then you could have the coil size as a function of n for the excluded volume chain with this term. So you do that, if you do that, you find this equation, which is kind of messy. Then you say that the fifth power is much bigger than the third, so you throw away the third, and you end up with this expression, which is that the coil size goes with the end of the 3/5 instead of 1/2. Right, so that's the excluded volume chain idea, end of the 3/5 versus 1/2. In other words, 3/5 end of the 3/5 is bigger than end of the 1/2. Depending on what n is, it could be a big difference. All right, so that was the Floyd-Krigbaum business, right? If you plot that, right, so you can also all right, so you can also just do a numerical integration of this thing. So like you can calculate this thing for every value, plot it as a function of n. So calculate this for a bunch of n's, and then integrate that r squared times that, right? And then you can actually get the mean squared end-to-end distance by numerical integration, which should be accurate, right? So that's the red dots here. Numerical integration of that thing for various molecular weights, and you find out it goes to a power, at the beginning it isn't a power law, up to about 100, which is like where we define a polymer anyway. And then it turns into a power law. Log is a, so if it was Gaussian, it would follow this purple power 2. And then our prediction of 5/3 is this blue line, it like overshoots it. Then the actual slope of this thing is 1.72. And then the computer simulations give something like 1.70. So typically you'll see not df for some reason. You'll see 1/df, which is new, because Flory originally didn't know about fractal dimensions. So he calls it new, and he calls it the scaling factor. If he turn it upside down, he would see this dimension, which would have had some meaning. Instead, they have this scaling factor new, which just looks like a V, right? So anyway, so new for this for 5/3 is 1.6, and new for the 1.7 is 0.588. You'll see like that's like a magic number in polymers of 0.588 for the scaling factor, which means 1.70. And then this 1.72, which is the actual integrated value, so that comes from computer simulation of 0.588. This is like 0.58. And there's, all right, believe it or not, between 5/3, so this would be 1.67. So there's been a lot of arguments between people talking about whether it's 1.67 or 1.70. And nobody mentions that it actually is 1.72 if you actually do the calculation, right? So anyway, that's kind of the way things go. People argue about things like whatever it is, 0.05 difference of something. But so anyway, that's kind of the Floyd-Krigbaum. The next thing is to look at how you include the temperature dependence. So this is basically the hardcore exclusion, like the B term and the van der Waals. So you want to add in the temperature dependence, which you can do. So it takes probably like 10 minutes to do that. But so anyway, I'll leave it there for now, this thing. Next, like on Wednesday, I'll go through the temperature dependence part of this thing.